Hello, Algebra. We're going to do a new lesson today, lesson chapter 11, lesson 1. And today we're going to talk about a new type of relationship and equation that we haven't seen yet, and that's an inverse variation. Okay, an inverse variation is a relationship between two values that always remains the same when you multiply them. So notice here would be one example. If you take x times y, you get 16, right? And you take x times y, you get 16. So notice in these pairs in this relationship always can be multiplied together to give us 16. That would be an example of an inverse variation. Inverse variation equations can be written in two different ways. Both are acceptable today as you write them. Either y equals k divided by x, or even easier, x times y equals k. Okay, and so k would be this amount that they multiply together to get. Now, just as a review, this is the type of a relationship that we've already worked with quite a bit, right? You're familiar with this equation, y equals k times x. Now, that's a direct variation equation, where if you take something times the x, you get a certain value for the y, right? So notice here would be a direct variation relationship that you're very familiar with. Notice in each of these pieces, we're taking x times 3 to get our y, right? And so notice you can't multiply the pairs together. 1 times 3 equals 3, 2 times 6 is 12, 4 times 12 is 48, right? They don't equal the same. So that's how you can tell the difference between a direct variation equation and our inverse variation equations that we're going to look at today. So one of the first things they're going to have you do is they're going to have you look at tables and equations, and they're going to ask you, is this one of these new inverse variations, or is this a direct variation? Okay. Remember, if it's an inverse variation, that's our new one for today, you can always multiply the pairs together and get the same answer. Can we do that on this one? 10, 1 times 10 is 10, 2 times 5 is 10, 5 times 2 is 10. Yes. So this is an inverse variation. And they're going to have you explain today. Simple ways to explain would be, yes, all the pairs multiply together to get the same number. Would be probably the easiest way to explain that today. How about this table right here? Is this a direct variation equation or an inverse variation set? Take a look. Notice I can't multiply them all to get the same thing. So that rules out the inverse right away, right? They multiply together to get different products. But it is a direct variation equation because every time we're doing the same thing to the x to get our y, right? Notice what we're doing is we're taking it times 1/2, times 1/2, times 1/2, right? So if you ever see that relationship where something's always being done to the x to equal the y, then it's a direct variation equation. And so then to explain that one, the easiest way to explain that one, our book says, is to say it can be written in this form. Or in other words, you're always doing the same thing to the x to get the y. It would be another way to explain it. But the way our book explains it is it can be written in y equals k times x form. In other words, this one would be written like this, y equals 1/2 times x, right? So if that's an easier way to explain why it's a direct variation equation, you can use that explanation or say that it can be written in this form. Okay, sometimes they'll just give you an equation and they'll say, what kind of relationship is this, an inverse or a direct variation? And anytime you see x, y together, okay, remember x times y equals k is one of the inverse variations, ways to write that type of relationship, right? So if you ever see an x and a y right next to each other being multiplied times each other, that's an inverse variation, okay? So if you do see that going on, and the way you can explain that is, notice I can write it in this form really easily, right? All I'd have to do is divide both sides by -2, and I get xy equals 10. So I know it's an inverse variation because it can be written in this form. That would be an easy way to explain it. It can be written in xy equals k form. How about this one right here? Is this a direct variation, our older ones, or this newer one, an inverse variation? Notice this one, if I just flip-flopped it around, can be written in y equals k times x form, right? So that means it's a direct variation, right? We're taking something times our x to always equal the y, right? So this one, again, the explained part, just say it can be written in y equals k times x form. Okay, and then that's a very simple explanation to prove that it's a direct variation equation. Okay, then the next thing they're going to have you do is they're going to have you write inverse variation equations. Remember, there's two ways to do that. These are both correct ways to write an inverse variation equation. I prefer this one. I think it's just easier. You just take the x times the y to get the k, right? So it says, assume that y varies inversely as x. Here's that key word. If they said directly as x, then you'd write a y equals k times x equation, but it says inversely, right? So if y equals 18 when x equals 2, write an inverse variation equation that relates x to y. So all you're going to do is just grab your equation, right? We're going to write it like this, okay? Let's put our x and y in. X is 2, y is 18, equals k, right? So in other words, 36 equals k. And then just plug that k back into the equation, and you've got it. So here is our finished equation. So you always want to leave the x and y as x and y when you write the final equation. And then your k will be the part that's filled in. Okay, so x times y equals 36. That means the pairs must always multiply together to equal 36 because it's an inverse variation equation. Let's do one more like that just so you get the hang of it. Again, I prefer this way of writing it. I think it's easier. So notice it says, assume that y varies inversely as x. Here's the key word, right? If y equals 5 when x equals negative 4. So let's just fill in those pieces, right? If y equals 5, x equals negative 4, there we are, right? I get negative 20 equals k, so I'll just plug that back into this. xy equals negative 20. That means all the pairs of this relationship will multiply together to give us negative 20. Sometimes they're going to have a missing number in a relationship that you have to solve. So notice it says assume that y varies inversely as x. Sorry about that, I have the wrong word there. It should have said inversely. Assume that y varies inversely as x. If y equals 3 when x equals 12, find x when y equals 4. So here's a little simple equation they give you to solve problems like this. When they give you one pair and then a pair that's got one missing, you can use this simple equation to solve. Remember, in an inverse relationship, the sets of numbers always multiply together to give us the same answer, right? So notice our first set. We have 3 times 12, right? x1 and y1, right? Our first set of x's and y's, which equals 36, right? And then our second set, that we don't have x, but we have y, right? So what would be the really simple way to solve this? They both have to equal 36. Well, I can divide both sides by 4, and I get 9 equals x. And so that must be our missing 9. Hopefully that makes some sense. Would you really need this equation? Not necessarily. They're just showing you that you'd multiply the first pair together, and it's got to equal what that second pair equals. So they usually give you one number, so you can usually figure out, what is this missing number right here in that equation. So notice again, I made a mistake. I should say inversely. I apologize. I just copied and pasted from the previous one, and the mistake stayed. So assume that y varies inversely as x. If y equals 4 when x equals negative 8, find y when x equals negative 4. So notice we have our first pair. We have negative 8 times 4, right, our first xy. And then we have our first x, but not our other y, right? So this side equals negative 32 when I multiply that pair together. That means this side must also equal negative 32. Now you probably can guess that y is going to be 8, or you can divide both sides by negative 4, and you're going to see that y does equal 8. Okay, so that's how you solve those ones where you have a pair, and then a pair where one is missing. Set it up that way and solve for that equation. Here would be a real-life application of this, and I'm going to let you know this is very much like number 12 today, so it might make some sense to do this one after do number 12 after you've watched me do this one. It says the speed of a hockey puck is inversely related. So there's that key word that we know we're going to use, this equation, right? Excuse me, this equation. There we go. It says suppose a hockey puck with a mass of 164 grams is hit so that it accelerates at this speed. Find the acceleration of a 158-gram hockey puck if the same amount of force is applied. In other words, if you've got a really heavy hockey puck, you can't hit it very fast, right? And the opposite or the inverse is true. If you've got a little light hockey puck, you can hit it really fast, right? And so they're inversely related. They're opposites of each other. So it's a relationship where they're always opposites. And so as the mass goes down, the speed goes up. And as the speed goes up, the mass goes down, right? And so we've got our two pairs. Do you see that? This is like x times y equals x times y, right? We've got a 164-gram hockey puck going 122 meters per second, okay? And we've got a 158-gram hockey puck that we don't know how fast it's going, right? And so we're going to solve this, right? So very simply, we can just do 164 times 122, and I'm just popping that into a calculator nearby. You can do the same. That gives me 20,008 equals 158 times x, right? So I can divide both sides by 158, which gives us about 126.6 if I round to one decimal place, meters per second squared as far as the acceleration. So you see how we set that up? We put our first pair of numbers here, put our second pair here with the missing one, and then we just solve for x. So number 12 you'll do almost identically to that. Okay, they throw a lot at you today, as you can see. There's the last piece, last little thing. They're going to have you graph inverse variations. These are kind of funky. I'm going to show you how to do these. So it says graph an inverse variation. Again, there's our keyword, right? So we're thinking, okay, it's got to look like this, in which y equals 8 when x equals 3. So let's just write our quick equation, okay? And so x times y equals k, right? So 8 times 3 equals k. In other words, 24 equals k. So in other words, xy equals 24, right, is our final equation. So in other words, x times y always have to equal 24. And so what you're going to want to do is make an xy table. Give yourself plenty of spaces here. And what you need to do is you need to figure out pairs that you could multiply together to get 24. Okay, for instance, we could do 3 and 8. We could do 4 and 6, right? You can't ever do 0, right? 0 won't ever work because something times 0 is always 0. So we're going to skip 0 on our graph. I'll show you how that works. But don't only think of positive numbers or positive pairs. Get a few positive pairs, certainly. Let's do one that's not quite so big. How about like 2 and, yeah, how about 8 and 3, the opposite way? There we go. Okay. And then do 3 pairs of negative numbers too, okay? So let's do like -2 and here, let's do -3 and -8. I'm just thinking of numbers that'll fit on our graph. And -4 and -6 and -6 and -4, right? And so notice what's going to happen. If I graph this, 3, 8 would be my first one. Put a dot there. 4, 6 would be my second one. Put a dot there. And then 8, 3 would be my third one. Notice what it does. It creates kind of this J-shaped graph that goes like this. And then notice what happens now when I graph my negative ones. -3, -8. I'm going to end up with kind of a mirrored image of this. -4, -6. And then -6, -4. Do you see how I'm kind of ending up with an opposite example of this? And so notice I kind of get this opposite curve that sort of mirrors this one that I did over there. And so do you see how it's almost like it's looking at itself in the mirror? Basically, you're going to end up with a curve on your positive side of your graph and a curve down here on your negative side of the graph, and they'll mirror each other if you did it correctly. Look like it's looking at itself in the mirror. Okay, so that's how you graph inverse variations. Let's do one of each type of problem with you for your assignment. So let's do number 1. Is this an inverse or a direct variation? So if I multiply the pairs, I get 2 and then 32. So it definitely doesn't work for inverse. Is it a direct variation equation? Must be, because that's the only other option, right? It's a direct variation, you'll write. Okay, and then explain. Well, how can you explain? Because you can write it, you can just say you can write as y equals, what are they doing to the x each time? 2 times x, right? So there's my explanation. You can write it like that, right? They're just taking the x times 2. Make sense? How about letter number 4? If you think through our direct variation equation options, right, and our inverse variation equation options, remember our inverse variation equations can be written like this, or like this, and our direct variation equations look like this, right? Which one of these types of equations, either these two or this second one, can I write that number 4 as? Notice if notice dividing by 10 is the same thing as taking something times 1/10, right? That would be the same thing. So since I can write it like that, that's just like this, right? That's a direct variation equation. So you'd say direct variation, and then your explanation could be you can write your equation like this. All right, let's do one of the ones where you have to graph. We'll do number 5 right here. And then don't forget to put this on graph paper, okay? Hopefully you're still doing okay with your graph paper supply. I'll put a link again up on this lesson so you can print some more out if you need it, okay? So remember how to do this. We want to write an equation first, then we want to graph, okay? So we'll get our XY chart here. Remember, we want to do at least 3 positive and 3 negative to get our J-shapes or our curves in the right spots. All right, so I guess I'll need one more spot then if I need 3 of each. So x times y equals k, so 8 times 6 equals k. In other words, 48 equals k. And so y times x equals 48 is our equation, right? All right, so now we need the pairs of numbers that multiply together to give us 48, and they need to be small enough that we can graph them on our graph paper. I think the graph paper you guys have is a little bigger than mine, so I might struggle to get a few pairs on here, but I'll try my best. Like let's say like 6 and 8, right, would be one pair. I'm going to have trouble getting a lot of these on. 12 and 4. Here's a thought. I'm going to make my graph go up by 5s. I think that'll work a lot better. 35, and then, so just think of my graph as going up and down by 5s. There, I got them all labeled. That'll help. I would do the same with your graph paper too, is make it 5s, and it will fit better. So now we can more easily grab, a bigger pair. So how about like 48 and 1, right? Or 1 and 48 would certainly work too. All right, let's grab at least 3 negative pairs then. Again, you can just reverse the ones that you did already. That's fine. -4, -12, how about like 2, or how about -8 and -6? I just reversed those. So those are all pairs that equal 48, right? And so let's just graph them. We should end up with 2 J shapes. So 6, 8, would be about right there. 12, 4, would be about right here. 48, 1 would be tough to graph, but we can do 148 pretty easily. 35, 40, 45, yeah, it'd be about right here. And you can see our J shape that's forming, right? It's going to be kind of like that. It won't ever go to the 0, obviously, right? And so we graph that. And then we should end up with kind of an opposite U shape on the other side. Let's do that. So I'll use a red pen to graph our negative pairs. So -6, -8 would be, about right here. -4, -12 would be about right here. -8, -6 would be, approximately, about right here. And so you can see we're getting that opposite. If we did -1 and 48, that would really help us get, kind of another piece. -1 would be like here. So you can see that we're forming this opposite curve here. And so you see how it mirrors itself. So this would be number 5. I would recommend for number 5 going up by 5s. I think that's going to make you be able to fit enough dots to see your curve. You need enough dots to give, so you can figure out where it's curving. And so you might have to adjust your graphs a little bit to give you enough to see that. All right, one of these problems where you have one pair and you're missing the second pair. Remember this? X1 times Y1 is going to equal X2 times Y2, right? So we've got one pair. We've got a pair of 8 and 4. It's as if, assume that they vary inversely, right? Y equals 8, X equals 4. So 4 times 8 equals, and then we've got Y equals 2, X times 2, right? And so notice this side's 32, which means this side must also be 32. And you can probably already tell that X is 16, but if you need to divide both sides by 2 to tell that, there you go. So that would be number 9. Hopefully that gets you going on your assignment. I know they threw a lot at you today, but I don't think it's anything that's too crazy hard. But certainly if you get stuck or if something that I said didn't make much sense, don't hesitate to contact me. You guys have been doing really well with learning from home and watching the videos and figuring it all out. I'm proud of that. Keep that up, okay? Have a good day, guys.